November the 2nd, 2025, 6 days ago. NASA made a move that instantly caught the world's attention. It activated the Planetary Defense protocol for 3I Atlas. This wasn't part of routine skywatching. These protocols are only triggered when an object behaves in ways that raise red flags, sudden shifts in trajectory, mysterious bursts of acceleration, or brightness changes that don't fit any natural pattern we know. NASA doesn't scare easily. For decades, they've tracked thousands of asteroids and comets with precision. Their software can predict orbits years, even decades ahead. And their systems for handling near-Earth objects are some of the most advanced on the planet. Yet, despite all that, the Planetary Defense Alert has been issued fewer than 10 times in the last 20 years. And when it has, it was always for familiar objects. Bennu, Apophis, asteroids we've studied up close that move exactly as expected. 3I Atlas, though, doesn't behave like that. On November 2nd, NASA officially activated the Planetary Defense Protocol for 3I Atlas. In the hours that followed, the International Asteroid Alert network was mobilized. A special task force was formed, uniting astronomers from the United States, Europe, Japan, and China, and data began flowing rapidly between observatories around the globe. The reason was simple but deeply unsettling. 3I Atlas was acting in ways no natural object should. Its movements were erratic, its brightness unpredictable, and with its close approach to Earth set for December 19th, just 6 weeks away, any sudden shift in its trajectory could have serious consequences. NASA needed answers. Fast. There was no press conference, no dramatic headline, no breaking news moment. Instead, NASA quietly released a technical circular through the Minor Planet Center, the official hub for asteroid and comet data. Labelled MPEC 2025 VITHRA 2, the notice called on all observatories capable of tracking 3I Atlas to begin immediate and continuous monitoring through December. It mentioned unusual non-gravitational accelerations and unpredictable brightness variations, calm, clinical words that hinted at something far more mysterious. At first, almost no one noticed. The circular NASA released wasn't written for the public. It was dense, technical, the kind of language only astronomers understand. But inside the scientific community, the reaction was instant. Observatories that had been casually tracking Atlas suddenly switched to full-scale monitoring campaigns. Amateur astronomers with powerful backyard telescopes started coordinating observation schedules, ensuring that someone, somewhere, was always watching. Meanwhile, researchers who specialize in comets and interstellar objects began digging through months of archived data, trying to find a clue, anything that might explain why NASA was treating 3I Atlas like a potential threat. Then, on November 3rd, Newsweek broke the story to the world. Their headline was stark. NASA triggers Planetary Defense Protocol in response to unusual behavior from Comet 3I Atlas. The article cited anonymous sources inside NASA, describing the comet's behavior as erratic and inconsistent with natural models. It mentioned speed fluctuations near perihelion, unexpected brightness spikes seen by solar monitoring satellites, and trajectory deviations that hinted at forces acting on the object, forces that weren't gravitational. The Newsweek article avoided using the word threat, at least directly. It reassured readers that 3I Atlas wouldn't come anywhere near Earth. Its closest approach would be 1.8 astronomical units, or about 270 million kilometers away. Far too distant for any real danger. But the tone told a different story. Phrases like unprecedented behavior, defying predictions, and international coordination carried a quiet tension. The piece ended with a single, cautious quote from an unnamed NASA official. "We're monitoring the situation closely and coordinating with international partners to ensure we understand this object's trajectory and behavior." Within hours, the story spread everywhere. CNN aired an interview with Darryl Seligman from Michigan State University, who reminded viewers that interstellar objects are notoriously unpredictable, simply because we've observed so few of them. Fox News, meanwhile, spoke with Avi Loeb, who was far more direct. He suggested that the activation of planetary defense protocols meant NASA was seriously considering that 3i Atlas might not be entirely natural. By that evening, social media was on fire. Hashtags like 3i Atlas and planetary defense were trending worldwide. Inside astronomy forums and online observatory groups, heated debates broke out. Was NASA just being cautious, or was there something they weren't telling us? The International Asteroid Alert Network, or IAN, was created in 2014 by the United Nations Committee on the Peaceful Uses of Outer Space. Its mission is simple but vital: to coordinate the world's response if an asteroid ever poses a real threat to Earth. The network connects nearly every major space agency on the planet: NASA, the European Space Agency, and counterparts in Russia, China, Japan, and India, along with dozens of observatories and research centres. When IAN is activated, it acts like a global nervous system. Data is shared instantly, observations are synchronised to eliminate blind spots, and if an object looks dangerous, experts begin running impact simulations to model what might happen and what humanity should do next. But IAN isn't triggered often, it's been called into action only a handful of times, and always for credible impact risks. In 2019, it briefly went active for asteroid 2019 OK, which skimmed past Earth at just 77,000 kilometres, alarmingly close with only days of warning. In 2021 it was reactivated for Apophis, a massive asteroid expected to pass extremely close to Earth in 2029, requiring careful tracking to ensure it doesn't slip into a gravitational keyhole that could redirect it toward us in the future. Those were near-Earth asteroids, bound to the Sun like everything else in our solar system. 3i Atlas, though, is something else entirely, an interstellar visitor, a traveller from beyond our cosmic neighbourhood, and its closest approach, at 270 million kilometres, poses no collision risk at all. So why activate IAN? The answer seems clear. NASA isn't worried about impact, it's worried about the unknown. The protocol's activation also set something else in motion: the creation of a special task force, a hand-picked team of scientists brought together for one purpose: to figure out what's really happening with 3i Atlas. This isn't just another data review committee. The group includes experts in orbital mechanics, comet dynamics, non-gravitational forces, and, most intriguingly, spacecraft propulsion. That last inclusion raised eyebrows. NASA doesn't normally bring in propulsion engineers to study comets, unless there's a possibility that the object's acceleration isn't entirely natural. Since November 2nd, the task force has been meeting every single day, analysing observations, running advanced trajectory simulations, and trying to predict where Atlas will be in the weeks and months ahead. At the heart of their concern is what happened on October 29th, when Atlas reached perihelion, its closest point to the Sun. Observations from solar monitoring satellites showed something shocking: a surge in brightness far greater than any model predicted. Normally, comets brighten as they approach the Sun because heat drives outgassing, jets of vapour and dust that reflect sunlight. The rate of brightening is usually predictable, following established curves based on a comet's size and composition. For Atlas, the model suggested a gentle climb to about magnitude 11 at perihelion. Instead, it suddenly blazed to magnitude 7 or 8, roughly 16 times brighter than expected. Something, or someone, had given it an extra push. Rapid brightening in comets isn't unheard of. It can happen naturally during what's known as an outburst, a sudden release of gas from beneath the surface when trapped pockets are heated and burst open. But outbursts come with a telltale sign: debris. When they occur, they eject massive plumes of dust and ice that spread out for thousands of kilometres and stay visible for weeks. That didn't happen with 3i Atlas. Data from GOES-19 and SOHO satellites showed the object brightening dramatically, yet it stayed compact, clean, almost eerily contained. There was no expanding debris field, no dusty halo, no plume, just a sharp spike in luminosity with no physical explanation. For scientists, that's deeply unsettling, because it doesn't match any known pattern of natural comet behaviour. Then came the second anomaly, when astronomers compared Atlas's actual position on November 1st With where it should have been based on gravitational models, they found a discrepancy, several thousand kilometers off course. The deviation was small on the sky, only about 0.01 degrees, but at that distance it's enormous. That kind of shift means one thing. The object's motion doesn't fully obey gravity. It's accelerating, slightly but undeniably, under some additional unexplained force. Non-gravitational accelerations in comets aren't mysterious on their own. They're usually caused by outgassing, jets of vapor escaping from the nucleus that act like tiny thrusters, slowly nudging the comet's path. The effect is gentle, but over time it becomes measurable. Astronomers know how to account for it, using models that estimate both the strength and direction of the outgassing based on a comet's observed brightness and activity. But with 3i Atlas, those models don't hold up. The acceleration detected around perihelion was far too strong. To explain the observed trajectory shift using normal outgassing, Atlas would have needed to vent enormous amounts of gas, enough to create huge visible plumes, yet none were seen. That's the puzzle that forced NASA's hand. If an object can accelerate without visible outgassing, then one of two things must be true. It's made of materials that behave unlike anything we've ever studied, something that somehow sublimates without releasing detectable gases. Or it's being propelled by something internal, something not natural. Neither answer is comforting. The first stretches the limits of known physics and chemistry. The second raises questions that NASA would rather not ask, at least not publicly. But with December 19th fast approaching, and the object still behaving unpredictably, NASA chose the safer path. Treat it as a potential threat and prepare for every possibility. On November 3rd, just one day after NASA's quiet activation of the Planetary Defense Protocol, Avi Loeb weighed in with a provocative medium post titled, "The acid test results are in." In it, he argued that the perihelion data all but confirmed his long-standing suspicion, that 3i Atlas isn't a natural comet at all. Loeb cited the rapid brightening, the absence of debris plumes, the unexplained acceleration, and even the object's blue hue at perihelion, claiming these were signatures of artificial technology. He wrote, "Natural comets don't accelerate without outgassing. They don't brighten 16 times faster than models predict without shedding debris. And they don't turn bluer than the sun unless they have internal heat sources hotter than the solar photosphere. The simplest explanation is that 3i Atlas has an engine." Within 24 hours, the post went viral. Millions of reads, countless reposts, and a flood of speculation. But it also triggered a strong backlash. Many astronomers criticized Loeb for jumping to conclusions based on incomplete data. They reminded the public that during perihelion, Earth was positioned on the opposite side of the Sun, which meant ground-based telescopes couldn't see Atlas directly. The only observations came from solar monitoring satellites, which aren't designed for precision comet studies and lack the resolution of dedicated observatories. Critics urged patience, arguing that once Atlas re-emerged into view in mid-November, high-quality imaging would likely reveal natural explanations for its strange behaviour. In other words, they weren't ready to call it a ship. Not yet. Yet, despite all the noise online, the protocol remains active. NASA hasn't lowered the alert level, nor has it released any reassuring statements suggesting that early concerns were exaggerated. Instead, the agency has chosen silence. Measured, deliberate silence. Official updates have been limited to short technical notes. Press inquiries are quietly redirected toward the upcoming observation campaigns, where NASA promises to share more once new data comes in. But to many observers, that silence speaks volumes. If the anomalies were simple, a calibration error, a dust jet, a quirk of observation geometry, NASA would have said so by now. They've had plenty of opportunities. Instead, the continued heightened monitoring, the daily coordination between international teams, and the refusal to declare all clear all point to one thing. They still don't know what they're dealing with. So for now, they're waiting, watching 3i Atlas as it moves through the inner solar system, gathering every possible data point. Because if the behaviour continues to defy the laws of nature as we know them, this won't just be another comet story. It will be something far greater and far stranger than anyone expected. To truly grasp why NASA pulled the trigger on the Planetary Defense Protocol, You have to look back at what happened during perihelion, the comet's closest approach to the Sun, on October 29th, 2025, just 9 days ago. On paper, it was supposed to be routine. As 3I Atlas neared the Sun, its surface would heat up, frozen gases would sublimate, and astronomers would observe the familiar uptick in activity seen with countless comets before it. Simple, predictable physics. But that's not what happened. Instead of the expected, they got a cascade of anomalies, readings and signatures that broke every model of comet behaviour we know. Part of the problem was geometry. When Atlas hit perihelion, Earth was on the opposite side of the Sun, placing the comet in solar conjunction, hidden completely behind the Sun's glare from our vantage point. In that position, even the world's largest ground-based telescopes were effectively blind. Anything within just a few degrees of the Sun's disk is swallowed by scattered sunlight in Earth's atmosphere. So, at the most critical moment, when the comet's heating, activity and behaviour should have been at their peak, humanity couldn't see it. Our best instruments were staring into daylight, while Atlas, on the far side of the Sun, began doing things no one could fully explain. But we weren't completely blind. By sheer luck, or timing, several solar observation spacecraft were in just the right position to catch 3I Atlas as it passed behind the Sun. These weren't traditional telescopes. They weren't even designed for astronomy. They were solar physics missions, satellites built to study the Sun itself. Each carries specialized instruments called coronagraphs and heliospheric imagers, which block out the Sun's blazing disk so scientists can photograph the faint outer atmosphere, the corona. These instruments are tuned for studying solar storms, coronal mass ejections and the solar wind, not comets. But occasionally, when a comet crosses their field of view, they record it too. And in late October, 3 different spacecraft did exactly that. Stereo A, NASA's Solar Terrestrial Relations Observatory, operating since 2006, caught Atlas between October 18th and October 30th using its Secchi instrument suite. SOHO, the Solar and Heliospheric Observatory, a joint NASA-ESA mission that's been running since 1995, tracked the comet with its LASCO coronagraph. And GOES-19, a newer geostationary weather satellite launched in 2024, which carries a small coronagraph for monitoring space weather, captured Atlas right at perihelion. These 3 independent missions, all with completely different instruments, angles and purposes, ended up providing the only direct visual record of 3I Atlas during the most critical phase of its journey. And what they saw would soon raise far more questions than answers. The images from those solar missions were analysed by Qicheng Zhang of the Lowell Observatory and Carl Battams from the US Naval Research Laboratory, 2 of the world's leading experts in cometary dynamics. Their preliminary report, released as a preprint on October 31st, described findings that didn't fit any natural comet model. The first red flag was brightness. Normally, a comet's luminosity increases as it gets closer to the Sun, following a predictable power law, roughly the inverse square or inverse cube of its distance. That's because as sunlight intensifies, more of the comet's surface heats up, causing ices to sublimate and reflect light. But 3 Atlas didn't follow that rule. Its brightness scaled with an inverse power of 7.5, an extraordinarily steep curve. In practical terms, as the comet moved from 1.5 astronomical units to 1.36, a distance change of only about 10%, its brightness increased by a factor of 15 to 20. Such extreme brightening is sometimes seen when a comet is breaking apart, when the nucleus fractures and exposes fresh layers of ice that erupt violently into space. But in those cases, you always see the aftermath: debris fields, dust clouds, and fragment trails that stretch for millions of kilometers and linger for months. Atlas showed none of that. The object stayed remarkably compact, a sharp point of light surrounded by only a faint tight coma just a few 100,000 kilometers wide. No plumes, no fragments, no chaos. In short, it brightened like something exploding, but looked as stable as a machine. The second anomaly was even stranger: its colour. Back in July and August, when 3I Atlas was still distant and cold, it appeared reddish, which is perfectly normal. Most comets are coated in dark, organic-rich dust that gives them that subtle red tint. Then, in early September, during what astronomers called the green glow event, spectroscopic readings detected emissions from diatomic carbon and cyanogen, molecules that fluoresce bright green when exposed to sunlight. Again, completely ordinary behaviour. But at perihelion, everything changed. Data from SOHO's LASCO and GOES-19 showed the comet turning distinctly blue, not just slightly, but noticeably bluer than the Sun itself. That shouldn't be possible. The Sun's visible surface, its photosphere, burns at about 5800 Kelvin. It literally defines what we consider white light. Anything that merely reflects sunlight tends to appear redder, because dust and gas in space scatter blue light away, just like Earth's atmosphere makes our sky blue and sunsets red. So for Atlas to appear bluer than the Sun, one of two things must be happening. It's emitting its own light, radiation from an internal heat source hotter than 5800 Kelvin, or it's reflecting sunlight unnaturally, through some surface or mechanism that selectively amplifies blue wavelengths while suppressing red. Either scenario defies conventional comet physics. Natural bodies don't turn bluer than the Sun unless something inside them is generating light, not just reflecting it. There are natural reasons a comet might look blue, but none that fit what 3i Atlas displayed. Typically, when a comet appears bluish, it's not because of reflected light, but because of molecular emission. Certain molecules, such as cyanogen, Cn, or diatomic carbon, C2, glow brightly in the blue and violet regions of the spectrum when excited by sunlight. But that kind of glow leaves a fingerprint, distinct narrow emission lines at specific wavelengths. The problem is, LASCO and GOES-19 aren't spectrographs. They don't resolve individual emission lines. They measure broadband colour, capturing light across wide wavelength ranges. And in those measurements, Atlas's blue signature wasn't narrow or line-specific. It was broadband, spread evenly across the blue portion of the spectrum, exactly what you'd expect from thermal radiation, not fluorescence. That means the light was likely coming from a hot surface, not glowing gas. And here's the issue. At 1.36 astronomical units from the Sun, solar heating can only raise a comet's surface to around 300-400 Kelvin, roughly the temperature of boiling water, enough to melt ice, not make it glow. Even during violent outgassing or explosive sublimation, that heat is rapidly vented into space. The surface never approaches anything near glowing temperatures. To emit blue light thermally, a surface would need to exceed 5800 Kelvin, hotter than the Sun's photosphere. For a natural comet, that's physically impossible, which leaves only one conclusion. If 3 Atlas really was radiating broadband blue light, it must have had an internal heat source, something generating energy independently of sunlight. And the only known things that do that are stars, nuclear reactors, or high-temperature propulsion systems. Avi Loeb didn't stop at colour. In his November 3rd post, he wrote, "The blue colour is the 9th anomaly in a growing list of properties that don't fit natural comet models. Dust should redden scattered sunlight. Cold surfaces should glow red. Blue means hot, hotter than the Sun." Which raises an obvious question. What power source could generate temperatures above 5800 Kelvin inside a comet nucleus? The answer might be technological, a fusion reactor, a fission pile, or propulsion systems using high-temperature plasmas. It was the kind of statement that instantly divided the scientific community, half intrigued, half furious. But Loeb wasn't wrong about one thing. The anomalies were stacking up. The third was all about motion. After perihelion, 3 Atlas should have settled into a predictable path, its trajectory shaped only by the Sun's gravity and the faint tugs of nearby planets. But when astronomers resumed tracking it on November 1st, they found something strange. The comet was ahead of its predicted position by roughly 5,000 kilometers. That might sound minor, almost negligible. At a distance of 200 million kilometers, it's a shift of less than 0.01 degrees, barely measurable. Yet for orbital calculations, that's huge. NASA's models are accurate down to a few hundred kilometers at most. When an object strays by thousands, it means one thing: an extra force is at work. Something, or someone, had given Atlas a subtle push. Non-gravitational forces in comets are nothing new. When sunlight heats a comet's surface, jets of gas burst from vents in the ice, acting like tiny thrusters. If those jets are concentrated on the sunward side, they push the comet slightly away from the sun. If they're on the far side, they push it toward the sun. When the jets are uneven, they can even alter the comet's spin and orientation, subtly changing its path through space. Astronomers can usually account for these effects by modelling the comet's outgassing rate, how much gas it's releasing and in which direction, based on its brightness and activity level. In other words, the more gas escaping, the more the comet should move off its predicted track. But with 3 Atlas, those numbers don't line up. To produce a 5,000 kilometre deviation after perihelion, Atlas would need to be venting gas at rates consistent with a comet 10 times brighter than it actually is. Yet its observed brightness, even during the dramatic perihelion surge, was only 2 to 3 times higher than expected, not nearly enough to generate the required thrust. In short, the math doesn't close. Either Atlas is somehow converting outgassing into propulsion with unprecedented efficiency, or there's another source of acceleration at work, something that isn't caused by escaping gas at all. This is exactly the point where NASA's Planetary Defense protocol stops being a formality and starts being common sense. Under normal circumstances, predicting a comet's path is straightforward. You calculate the gravitational forces from the Sun and planets. You add the expected non-gravitational forces from outgassing. Based on how active the comet looks, you get a reliable orbit. But with 3I Atlas, step 2 doesn't work. The amount it accelerated doesn't match how bright or how active it looked. That means the usual model, more gas, more thrust, breaks down. And when your model breaks down, your predictions stop being trustworthy. Now imagine that with an object that's on its way past Earth. Right now, Atlas's closest approach, 270 million kilometers, is perfectly safe. On paper, the impact probability is basically 0. But that's only true if the object keeps behaving the way it's behaving now. NASA's worry is the what-if part. What if Atlas has another unexplained acceleration in early December, just before it passes Earth? What if the next acceleration is stronger than the last one? What if it's in a different direction, one that nudges it slightly closer to Earth? Each of those is a low probability scenario, but none of them are impossible, and when you're responsible for protecting a planet, not impossible is enough to trigger higher alert. So NASA did the cautious thing. Activate the protocol, mobilize international observatories, get as much real-time tracking as possible, and reduce the uncertainty. Because until they understand what's pushing Atlas, they can't say with 100% confidence where it will be 6 weeks from now. And if you can't say that, you watch it. Constantly. Since its formation on November 2nd, the task force has been running intensive simulations to explore every possible what if. Their goal? To understand how different acceleration strengths and directions could alter 3I Atlas's path in the weeks ahead. So far, those results haven't been made public, but leaks suggest something intriguing. The simulations show that if Atlas experiences another acceleration similar to what was observed at perihelion, its December 19th Earth flyby distance could shift by tens of millions of kilometers. Most models predict it will drift farther from Earth, which is good news. But a few runs show the opposite, the comet moving closer, potentially coming within 200 million kilometers. Still safe, yes, but noticeably nearer than expected. NASA's concern isn't that Atlas will hit Earth. The odds of that remain effectively 0. The real issue is control, or rather, the lack of understanding behind it. If the object were governed solely by gravity, its orbit could be projected centuries into the future with mathematical precision. If it behaved like a normal comet, driven by predictable outgassing, astronomers could still forecast its path by monitoring its brightness and activity. But if Atlas is accelerating through unknown mechanisms, or even more unsettling under deliberate control, then all the equations break down. Prediction turns into guesswork. And when an object capable of altering its own trajectory is moving through the inner solar system, guesswork isn't good enough. There's another piece of the puzzle that has scientists uneasy, the brightness. During perihelion, 3I Atlas brightened dramatically. Some of that could be explained by normal outgassing as the comet heated up near the Sun, but the absence of visible debris makes that explanation incomplete. If the object is somehow producing its own light, whether through artificial systems or high-temperature internal processes, then its brightness becomes more than just an observational detail. It becomes a signal. In that case, every fluctuation in brightness could carry meaning, a sign of changing activity levels, power output, or even operational status. That's why NASA's task force is watching its light curve in real time. Continuous monitoring would give them early warning if Atlas's behavior shifts again, if, for instance, its luminosity suddenly spikes or fades in ways natural comets never do. The next critical checkpoint comes soon. On November 11th, just 4 days from now, Atlas will finally re-emerge from solar conjunction, becoming visible again in the pre-dawn sky. Dozens of observatories around the world are preparing for the moment. Telescopes large and small, all aimed at the same target. Those new observations will answer the questions hanging in the air. Does the blue colour remain, or has the object returned to its earlier red-green hues? Is the coma still compact, or has debris finally appeared? And most importantly, is the trajectory deviation continuing, or has Atlas settled back onto a purely gravitational path? The answers to those questions will decide what happens next. If everything looks normal, the Planetary Defense Protocol may quietly be stood down. But if the anomalies persist, if Atlas keeps defying physics, then this story is only just beginning. The Planetary Defense Coordination Office, headquartered at NASA's Washington, D.C. facility, might sound like a small department, but when it activates, the entire world feels it. Its reach extends across continents, linking dozens of agencies, observatories, and research centres in a global network designed for one purpose: to safeguard Earth from celestial threats. To understand the weight of the 3i Atlas activation, you first have to understand the infrastructure NASA has spent the past decade building. Formed in 2016, the Planetary Defense Coordination Office, or PDCO, unified efforts that had previously been scattered across NASA's various divisions. Its mission is clear and uncompromising: detect near-Earth objects that might pose an impact risk, characterize their orbits, size, and composition with precision, coordinate international response efforts if a credible threat is identified, and, if necessary, develop mitigation strategies, whether that means deflection missions or, in the worst-case scenario, evacuation planning. Behind the scenes, the PDCO maintains vast databases of known asteroids and comets, some tracked for decades. It funds a worldwide network of survey telescopes that sweep the night sky, searching for new intruders. It also oversees simulation exercises, stress testing the systems and communication pipelines that would activate in a real impact scenario. So when that office, built to respond only to genuine threats, triggers its protocol for an object like 3i Atlas, which poses no known risk of collision, it sends a clear message: NASA isn't reacting to hype. It's reacting to anomalies that have resisted every conventional explanation so far. In the 9 years since it was established, the Planetary Defense Coordination Office has never had to activate its full response protocols for a genuine ongoing threat. There have been close calls, yes, moments that tested the system, but nothing that warranted a global mobilization. In 2019, asteroid 2019 OK passed just 77,000 kilometers from Earth, closer than some of our satellites, and it was only discovered a day before the flyby. That near miss sparked serious reviews of the detection network. Then, in 2020, asteroid 2020 VT4 slipped by even closer, just 400 kilometers above the geostationary orbit line, the closest recorded asteroid approach in history. But in both cases, by the time the objects were detected, they were already past Earth. There was nothing left to coordinate. No response, no alert, just post-event analysis. 3i Atlas, however, is an entirely different story. It was detected months in advance, long before perihelion, giving astronomers time to refine its orbit and study its behaviour. Its projected path doesn't come anywhere near Earth. The closest approach, around 1.8 astronomical units, is a safe 270 million kilometres away. Under any normal circumstance, this would have been treated as a scientific curiosity, not an emergency. Observatories would observe it occasionally, publish papers, and move on. But that's not what happened. NASA's decision to activate planetary defense protocols for an object so distant and supposedly harmless makes one thing clear. This isn't about impact risk. It's about unpredictability, the possibility that Atlas isn't behaving under the same rules as everything else in the solar system. And when something stops following the rules of gravity, even from 270 million kilometers away, NASA pays attention. As part of NASA's Planetary Defense Protocol, the International Asteroid Alert Network, IAN, was also fully activated, a signal that the situation had moved beyond ordinary research. The IAN is a coalition of more than 30 institutions across 18 countries designed to function as a global early warning and tracking system. Its members include some of the most capable observatories and space research centers on Earth. NASA's Jet Propulsion Laboratory in California, which specializes in orbital computation and trajectory modeling. The European Space Agency's Near-Earth Object Coordination Center in Italy. Japan's Space Guard Association, dedicated to asteroid detection and impact prevention. Russia's Institute of Applied Astronomy, a key player in orbital tracking. China's Purple Mountain Observatory, one of Asia's leading astronomical facilities, and India's Physical Research Laboratory, which contributes advanced optical and radar data. Each organization brings something vital to the table: telescopes, computational models, observation time, and decades of collective expertise. When IAN is activated, every member commits to prioritize the target object, share all data in real time through secure communication channels, and coordinate observation schedules across time zones to maintain uninterrupted global coverage as Earth rotates. For 3i Atlas, that activation meant the start of one of the most comprehensive monitoring campaigns in recent memory. In the Northern Hemisphere, observatories such as the Lowell Observatory in Arizona, the Nordic Optical Telescope in the Canary Islands, and the Multiple Mirror Telescope collaboration in Massachusetts are now tracking Atlas during the pre-dawn hours when it's faintly visible near the horizon. Meanwhile, in the Southern Hemisphere, where the comet sits higher in the sky, facilities like Cerro Tololo in Chile, Siding Spring Observatory in Australia, and the South African Astronomical Observatory have committed significant telescope time to continuous monitoring. For the next several weeks, those observatories will work in relay, one handing off to the next as night falls across the globe, ensuring that 3 Atlas is never out of sight. Even amateur astronomers have been drawn into the effort. The International Asteroid Alert Network includes an amateur outreach division, recognizing that many highly skilled observers with large backyard telescopes can make critical contributions, especially when an object's behavior changes quickly and needs high-cadence monitoring. At its current brightness of magnitude 11 to 12, 3i Atlas is well within reach of advanced amateur telescopes, typically in the 8 to 12-inch aperture range. And since early November, dozens of amateur astronomers around the world have been submitting their nightly data. Precise position measurements, brightness readings, and even colour estimates. Their efforts effectively fill the gaps between major observatories, creating a global, near-continuous observation network. That network ensures that if Atlas suddenly flares, fades, or shifts position, even briefly, someone, somewhere, will catch it. Meanwhile, the task force that NASA established on November 2nd operates at an entirely different tier. While the IAN coordinates observations, this smaller specialized group is responsible for interpreting the flood of data and advising NASA leadership and international partners. Roughly 20 experts are divided into 3 working groups, each focusing on a different aspect of the problem. The first group handles trajectory analysis, the most urgent priority. They use incoming data from observatories and amateurs alike to constantly refine Atlas's orbit and simulate its future motion. By running thousands of computational models, they're exploring how various strengths and directions of non-gravitational acceleration could alter its path over the coming weeks and months. Their findings feed directly into the decisions that determine how long the Planetary Defense Protocol remains active, and how seriously NASA treats the possibility that something about 3i Atlas still isn't following the rules of nature. The second working group within the task force is focused on physical characterization. understanding what 3i Atlas actually is. These researchers are diving deep into spectroscopy, photometry, and high-resolution imaging data to analyze the comet's composition and how it's evolving over time. This team includes comet specialists, spectroscopists, and thermal modelers, each tackling a different piece of the puzzle. Their mission is straightforward but enormously challenging: determine whether the anomalies observed at perihelion can be explained by some exotic yet natural composition, or whether the data rules out natural causes entirely. They're looking for chemical fingerprints, specific emission lines that could point to rare materials or unknown compounds, and for thermal signatures that might suggest artificial heat sources. If they can isolate a pattern that requires high-temperature processes or engineered materials, it would mark nothing less than breakthrough evidence of a technological origin. Then there's the third group, and it's unlike anything NASA has assembled for a comet study before. This team brings together aerospace engineers, spacecraft propulsion experts, and even military analysts experienced in tracking and identifying artificial satellites. Their assignment is delicate and potentially explosive. They're tasked with determining whether 3i Atlas's motion matches the profile of controlled propulsion. If it does, what kind? They're dissecting every trajectory deviation, calculating the implied thrust magnitude and direction, and comparing the data against all known propulsion technologies, from conventional chemical engines to ion drives, plasma thrusters, and fusion-based systems. They're also modelling what kind of engine configuration could physically fit inside an object roughly the size of a small asteroid, tens to hundreds of meters across, and still produce the accelerations observed. For now, none of their findings have been made public, but the very fact that such a team exists and that NASA assembled it quietly, without press briefings or announcements, suggests they're preparing for possibilities far beyond standard comet physics. The inclusion of propulsion experts in a planetary defense task force is something NASA has never done before. In every previous case, whether studying comets, asteroids, or interstellar visitors like Oumuamua and Borisov, there was no need for such expertise. Those objects behaved like what they were, natural bodies following the laws of physics. But 3 Atlas has rewritten that rulebook. Its motion, its unexplained accelerations, and its light signature, possibly indicating internal heat sources, have forced NASA to confront scenarios that would have sounded like science fiction not long ago. When an object accelerates without visible outgassing and emits light that suggests temperatures hotter than the sun, asking whether that behaviour could be consistent with artificial propulsion stops being sensational, it becomes a legitimate scientific inquiry. To manage this process, the task force now meets daily via secure video conference. With participants scattered across multiple time zones, the meeting times rotate, sometimes morning in California, evening in Europe, or midnight in Japan. These sessions are officially designated as pre-decisional, meaning the discussions and preliminary findings are classified within NASA until they've been verified and approved by agency leadership. That internal classification has, unsurprisingly, sparked public speculation, whispers that NASA is hiding something. But the reality is far more procedural than conspiratorial. Pre-decisional simply means that early interpretations aren't ready for public release. In science, premature announcements can backfire. When conclusions shift, as they often do with new data, it creates confusion, fuels misinformation, and damages trust. So NASA is doing what NASA always does when confronted with uncertainty: collect data first, speak later. Despite NASA's silence, information has started to leak, and those leaks have only deepened the mystery surrounding 3i Atlas. On November 4th, an anonymous insider described as familiar with the task force discussions spoke to a science journalist. According to this source, the team's trajectory simulations indicate roughly a 15% probability that Atlas will experience another acceleration event before its December 19th flyby. If that happens, the object's approach distance could shift by as much as 50 million kilometers, either closer or farther from Earth. The source was careful to emphasize that even in the worst-case scenarios, a collision remains impossible. The risk isn't impact, it's uncertainty. Each unexpected acceleration complicates observation scheduling, spacecraft tracking, and potential mission planning. When a celestial object stops behaving predictably, even the logistics of pointing a telescope at the right spot in the sky become a moving target. A second leak, published by a popular space news blog, hinted at something even more provocative. Citing unnamed members of the Physical Characterization Group, the report claimed that the team had found spectral features in the perihelion data that don't match any known cometary molecules. Normally, natural comets show strong ultraviolet emissions from familiar compounds, hydroxyl radicals, carbon monoxide, and a handful of organic fragments. But in Atlas's case, the ultraviolet spectrum reportedly contained extra peaks that don't correspond to anything in standard comet chemistry databases. The blog speculated cautiously that these signals might represent industrial byproducts or propellant residues, artificial compounds produced by high-temperature reactions or exhaust systems. Still, without access to the actual data, there's no way to confirm that claim. Whether those mysterious emission lines turn out to be simple calibration errors or the first fingerprints of something engineered, one thing is certain. Atlas refuses to behave like a comet, and the world's scientists are running out of natural explanations. NASA has neither confirmed nor denied any of the recent leaks. Officially, the agency's position remains cautious and consistent. Observations are ongoing, data analysis is underway, and conclusions will be released only when the evidence is clear. In a brief statement to reporters on November 5th, Administrator Bill Nelson offered a calm reassurance, but his wording raised eyebrows. "We're watching this object very carefully. It's exhibiting some behaviours we want to understand better. That's why we've activated our coordination protocols and are working with international partners. There's no immediate threat to Earth, but scientific curiosity demands we investigate thoroughly." At first glance, it sounded routine, measured, responsible, professional. But that phrase, scientific curiosity, carries more weight than it appears to. It frames the situation as academic, implying this is a matter of study, not concern. Yet the reality behind the scenes tells a different story. Activating the Planetary Defense Protocol is not something NASA does lightly. It's resource-intensive. Major observatories have cancelled or delayed scheduled research projects to dedicate telescope time to 3i Atlas. Teams of scientists are now working full-time, analysing incoming data instead of their usual research. International coordination meetings require diplomatic channels, clearances, and logistics, the kind of infrastructure reserved for genuine global priorities. In short, this isn't the kind of response triggered by curiosity alone. NASA's public tone may be calm, but the operational footprint, the manpower, the urgency, the scale, says something else entirely. They're not just studying a comet, they're treating 3i Atlas like a variable they don't yet understand, one they can't afford to ignore. The comparison to past protocol activations makes it clear just how unusual the 3i Atlas situation really is. The most significant prior activation came in 2021 for the asteroid Apophis, a 370-metre-wide object that will pass within just 32,000 kilometres of Earth on April 13, 2029. When it was first discovered, Apophis briefly carried a 2.7% chance of impact in 2036, the highest impact probability ever recorded for a known asteroid. That statistic alone was enough to mobilize NASA's Planetary Defense Coordination Office, trigger international observation campaigns, and justify activating full protocols. Over time, improved measurements ruled out the 2036 threat. But the 2029 flyby still poses a unique concern. During that encounter, Apophis will pass through what scientists call a gravitational keyhole, a narrow region of space where Earth's gravity could subtly alter its orbit. If it passes through the right spot, that shift could set up a potential impact on a future return. Tracking its trajectory with extreme precision is therefore critical to ensure it misses that invisible danger zone. In short, the Apophis activation was a case study in calculated risk management. There was a quantifiable impact probability, a defined mitigation timeline, and a clear, physics-based reason for heightened coordination. The uncertainty was about when and where, not what. 3i Atlas, however, is another kind of uncertainty altogether. There's no collision threat, no keyhole, no measurable risk curve. The problem isn't predicting whether it will hit Earth, it's understanding what it even is. Apophis was a known object behaving within the boundaries of classical physics. 3CI Atlas is something else, an object that doesn't fit the models, whose trajectory, luminosity and thermal behaviour all resist natural explanation. For Apophis, the question was how do we deflect it if necessary? For Atlas, the question is what are we even looking at? And that shift, from mitigation to comprehension, is what makes the current activation so extraordinary. This kind of uncertainty is far more difficult to manage than any collision threat. With Apophis, the worst-case scenario was tangible, a possible impact in 2036 or later. Engineers could run simulations, design deflection strategies, and build contingency timelines. The parameters were known, the physics familiar. With 3 Atlas, there is no defined worst-case scenario. If the object is under some form of control, what is controlling it? If it's technological, what are its capabilities? And what, if anything, does it intend to do? These are questions that the Planetary Defense Protocol was never built to answer, and yet by November 2nd NASA had concluded that these questions could no longer be ignored. All eyes are now on December 19th, the date of Atlas's closest approach to Earth. Every new data point before then, a shift in trajectory, a spike in brightness, or the appearance of new spectral features could add to the growing list of anomalies. The task force has reportedly been preparing a series of contingency plans for different outcomes. If brightness suddenly increases, which observatories will execute immediate follow-up imaging? If trajectory deviations occur, how fast can those be detected, modelled and confirmed? And if communication signals are detected, what frequencies should be monitored and what message protocols should be followed? It's that last scenario, communications monitoring, that's perhaps the most revealing. According to multiple reports, the task force has coordinated with major radio astronomy facilities to begin scanning 3I Atlas for any potential emissions in the radio spectrum. Among those enlisted are the Very Large Array, VLA, in New Mexico and the Parkes Observatory in Australia, 2 of the most sensitive radio telescopes on Earth. Both have already allocated observation windows in early December, when Atlas will be ideally positioned for long-duration radio tracking. The goal isn't to prove anything extraordinary, not yet, but simply to listen. If the object is emitting radio energy, whether deliberately or as a byproduct of internal systems, these instruments might detect it, and if they do, if even a faint structured signal emerges from that patch of sky, the implications would reach far beyond planetary defense. It would mean that 3I Atlas isn't just visiting our solar system, it's announcing itself. Now everything begins to converge. The Planetary Defense Protocol is still active. The task force continues its daily briefings. Every major observatory, professional and amateur alike, is tracking 3I Atlas with a level of intensity normally reserved for confirmed impact threats. And in just 6 weeks, on December 19th, the object will make its closest approach to Earth. It's not dangerous, not even close, but it's close enough that the entire astronomical community will be watching, and close enough that if anything happens, if Atlas alters its trajectory again, if its light shifts, or if new anomalies appear, we'll see them in real time. And that's the question NASA isn't answering, at least not publicly. What do they know that we don't? For context, that close approach is at 1.8 astronomical units, about 267 million kilometres. By comparison, Mars at its nearest comes within 55 million kilometres of Earth. The Moon is only 384,000 kilometres away. That means Atlas will still be roughly 700 times farther than Mars and more than 600 times the Earth-Moon distance. In other words, this is not a threat. Even if 3I Atlas were made of solid metal, even if it somehow defied its classification as a comet and behaved like an asteroid, no natural or artificial process could shift its orbit by hundreds of millions of kilometres in a matter of weeks. The Earth is safe. But safety isn't the question anymore. What has NASA seen in the data, in the spectra, in the trajectory plots that compelled them to mobilize planetary defense resources for an object that shouldn't need defending against? Whatever the answer is, we'll find out soon enough. On December 19th, as a 3I Atlas passes through the inner solar system, every major telescope on Earth and in orbit will be watching. and if the universe has something to show us, we'll be there to see it. But safety isn't NASA's only concern anymore. The upcoming December approach represents something far more critical. It's the final high-quality observation window before 3 Atlas disappears from reach. After this pass, the object will begin to recede from the inner solar system, fading quickly as it drifts back into interstellar darkness. By March 2026, it will be too faint for even the largest telescopes to detect, and once that happens, it's gone, lost to the void between the stars, possibly forever. That's why December isn't just another checkpoint. It's the last chance to find out what this thing truly is, to determine, once and for all, whether 3I Atlas is a natural interstellar comet or something else entirely. That urgency now drives every decision the task force makes. In the past 2 weeks, they've finalised a coordinated global observation campaign involving the most advanced instruments humanity has ever built, the Hubble Space Telescope, capable of ultra-precise optical imaging in visible and ultraviolet light. The James Webb Space Telescope, observing in infrared to detect faint heat signatures invisible to ground-based instruments. The Very Large Telescope in Chile and the Keck Observatory in Hawaii, providing high-resolution spectroscopy and rapid follow-up tracking from Earth. These facilities represent the pinnacle of modern astronomy. Securing time on any one of them requires months of review, multiple approvals, and intense competition from scientific projects around the world. Yet somehow, 3I Atlas has now been prioritised across all of them. Observation time that might have gone to studying exoplanets, supernovae, or distant galaxies has instead been reassigned to this single, enigmatic object, an icy traveller from beyond our solar system that refuses to behave like anything we've ever seen. The message is unmistakable. Whatever 3 Atlas is, the world's best scientists and its most powerful telescopes are determined to find out before it vanishes into the dark for good. In mid-December, the investigation reaches its climax. On December 15th and 16th, the Hubble Space Telescope will turn its gaze toward 3I Atlas, capturing high-resolution images across multiple wavelengths, from ultraviolet through near-infrared. The mission plan is ambitious, to map the comet's structure in unprecedented detail, searching for jets, plumes, or discrete surface features that might explain the comet's puzzling non-gravitational acceleration. At Atlas's current distance, Hubble's optics can resolve features only a few hundred kilometers across, sharp enough to reveal localized vents or heat sources if they exist. By measuring color gradients across the coma, Hubble will also test whether the intense blue emission seen at perihelion persists, or whether the object has reverted to the reddish-green hues typical of natural comet activity. Then, on December 17th, it's James Webb's turn. Using its near-infrared spectrograph as a NIRSpec and mid-infrared instrument, EMIRO, Webb will dissect the chemical composition of the gas and dust surrounding Atlas with exquisite precision. Its unmatched infrared sensitivity can identify molecular species invisible to optical telescopes, revealing what exactly is being released or produced near the surface. For natural comets, the spectrum is familiar: water vapor, carbon monoxide, carbon dioxide, methane, ammonia. But if Webb detects compounds that don't belong in that list, substances like hydrazine, nitrogen tetroxide, or other exotic high-temperature propellants, it would be a seismic discovery. Those chemicals require industrial-scale synthesis or engineered systems to exist. In short, Hubble will show us what Atlas looks like, Webb will tell us what it's made of, and between them, they may finally answer the question that has haunted this investigation from the start. Is 3I Atlas a comet, or something built to look like one? Throughout December, ground-based observatories will keep an unblinking eye on 3I Atlas, providing the continuous monitoring that even space telescopes can't sustain. At the forefront of this effort is the Very Large Telescope, VLT, in Chile, equipped with its state-of-the-art SPHERE instrument, a system originally designed to image exoplanets by blocking the glare of their parent stars. SPHERE uses a coronagraph to suppress bright light, revealing faint structures that would otherwise be lost in the background. For 3I Atlas, that same technique might do something never accomplished before. image the nucleus directly. Normally, a comet's nucleus is impossible to see. It's small, dark, and shrouded in a brilliant halo of gas and dust, the coma, that overwhelms any light reflected from the solid core. But SPHERE's ability to block the coma's glare could expose what lies beneath. If it succeeds, astronomers will, for the first time, obtain a direct measurement of the object's size and shape, crucial data for estimating its density and determining whether its structure matches that of a natural comet or something engineered. Meanwhile, another kind of observation will unfold just as 3i Atlas makes its closest pass. From December 18th through 20th, the Very Large Array, VLA, in New Mexico will conduct a 12-hour continuous radio scan on December 18th, followed by shorter sessions on the 19th and 20th. The VLA will survey frequencies between 1 and 10 GHz, a range that includes both natural astrophysical emissions and artificial transmission bands. Among them, the famous hydrogen line at 1.42 GHz, the frequency long favoured by SETI researchers as a potential channel for deliberate interstellar communication. The scan also covers frequencies used for spacecraft telemetry, navigation beacons, and radar systems. If 3i Atlas emits radio energy, whether by design, by accident, or as a byproduct of some internal mechanism, the VLA will catch it. And if that happens, humanity won't just be observing an interstellar visitor, it will be hearing from it. The Parkes Observatory in Australia will take over when the Very Large Array isn't watching, providing vital Southern Hemisphere coverage on December 19th and 20th. Known affectionately as the Dish, Parkes is one of the most sensitive single-dish radio telescopes on Earth, and it carries a long legacy of listening to the unknown. Back in 1977, Parkes was part of NASA's Voyager communications network when it detected several anomalous radio signals, transmissions that were eventually dismissed as interference, though never fully explained. Decades later, its receivers remain among the quietest and most refined in the world. If 3i Atlas emits anything, even a faint structured pulse buried in background noise, Parkes is perfectly positioned to hear it. But that's only the beginning of the story. If a signal is detected, the next steps are anything but clear. No protocol, not NASA's, not SETI's, has ever been tested under conditions like this. The SETI post-detection protocols drafted decades ago assume a distant signal, one arriving from light years away. In that scenario, humanity has time to confirm, to deliberate, to decide collectively how to respond. But a signal from 3i Atlas would be different. It wouldn't be distant. It would be right here, inside the solar system, a mere 267 million kilometres away and approaching. That changes everything. There would be no years, no months, perhaps not even weeks to prepare. The timeline would compress to days, maybe hours. Decisions about confirmation, public disclosure, and potential response would have to be made in real time. And the biggest question of all would land squarely on humanity's doorstep. Who speaks for Earth? In theory, the United Nations Office for Outer Space Affairs holds that authority. In practice, if a transmission were detected by NASA or its partners, the first voices heard would likely be scientists and engineers, trying to determine whether what they found is real. Because if 3i Atlas sends a signal, if it's intelligent, deliberate and near, there won't be time for debate. There will only be the moment, and whatever humanity chooses to say next. It's for this exact reason that the task force isn't made up solely of scientists. Alongside astrophysicists, spectroscopists, and propulsion engineers sit policy advisors and representatives from both the US State Department and the Department of Defense. Their presence signals that the discussions have moved beyond the purely scientific into the realm of strategy, diplomacy, and national security. Behind closed doors, the questions being asked are no longer theoretical. If 3i Atlas is under control, who controls it? If it's a probe, what civilization sent it, and why now? If it has been observing Earth, what has it already seen, recorded, or transmitted? And perhaps most unsettling of all, if it's approaching intentionally, choosing to pass relatively close to Earth rather than steering clear, what message does that send? These aren't the kind of questions that belong in scientific journals. They belong in classified briefings, policy discussions, and crisis simulations. the very environments NASA, the Pentagon and the State Department are now quietly coordinating. And it's not paranoia driving this, it's the data. Each anomaly on its own could have been brushed aside. The non-gravitational acceleration, the blue emission hotter than the sun, the spectral lines that don't match any known molecules, the hyper-precise trajectory corrections, the nickel-like spectral reflections indicating metallic composition. Any one of these could be explained by something exotic but natural. But taken together, multiple independent anomalies, confirmed by separate instruments, forming a consistent behavioural pattern, they paint a picture that's hard to dismiss as coincidence. In a matter of months, 3I Atlas has gone from a faint interstellar curiosity to an object that defies nearly every rule of cometary physics. And while no one at NASA will say it aloud, the pattern now sits uncomfortably close to the probability space of artificial origin, a possibility that, not long ago, would have been unthinkable. In his November 6th post, published just yesterday, Avi Loeb didn't hold back. He wrote, "Science advances when observations force us to update our assumptions. For decades, we assumed interstellar objects would be natural, debris from other planetary systems, ejected by gravitational interactions. Oumuamua challenged that assumption with its acceleration. Borisov seemed to restore our confidence with its ordinary cometary behaviour. But Atlas has brought us back to the question, are we alone? The Planetary Defense activation is an acknowledgement that we can't dismiss the technological hypothesis anymore. NASA is preparing for the possibility that December 19th will be first contact. That last phrase, first contact, landed like a shockwave. It's the language of science fiction, not scientific publications. Yet coming from Loeb, it carries a different weight. He's been here before, accused of sensationalism, criticised for speculation, but also vindicated for pushing boundaries that traditional science preferred to ignore. Loeb's argument is straightforward, and in its way uncomfortably logical. Science progresses by breaking assumptions, not defending them. Throughout history, paradigm-shifting discoveries began as heresies. Continental drift was mocked until plate tectonics proved it true. Heliocentrism was condemned until Galileo's telescope forced the issue. The Big Bang was once derided as mysticism until cosmic background radiation silenced the skeptics. Loeb believes extraterrestrial technology sits in that same category, an idea so disruptive, so existentially heavy, that the scientific community resists it instinctively, even when the data begins to point in its direction. In other words, it's not that NASA or astronomers don't see what's happening, it's that acknowledging it might require rewriting everything we thought we knew about our place in the cosmos. And that's what makes December 19th more than a scientific milestone. For some, it's shaping up to be a test, not of technology, but of belief. Critics have been quick to push back, reminding everyone that extraordinary claims require extraordinary evidence, and so far 3I Atlas hasn't crossed that threshold. The data is unusual, yes. It's inconsistent, yes. But anomalous isn't the same as artificial. Skeptics argue that natural explanations, however unlikely or convoluted, must be ruled out completely before invoking technology. Perhaps Atlas is a comet formed in a radically different environment, around a star with unusual metallicity or chemical ratios. Perhaps its ices and dust contain exotic compounds that alter its reflectivity and acceleration in ways that mimic artificial behaviour. It might simply be a 1 in a billion outlier, rare but still natural. Until those possibilities are exhausted, critics say, talk of first contact is premature. That debate, between open-minded speculation and scientific caution, will likely continue well past December. But the debate itself is no longer the focus. What matters now are the observations. The December 19th approach is the pivotal moment. What happens in those few days will determine which side of history this story lands on. If 3I Atlas executes another controlled manoeuvre, if it emits structured radio signals, if Webb spectrographs detect industrial compounds, or if Hubble captures geometric structures on its surface, then the case for technological origin becomes impossible to dismiss. But if none of those occur, if Atlas coasts silently past, its anomalies explained by chemistry and physics rather than intent, then the natural hypothesis endures. The object will fade into the dark, and humanity will file it away as another mysterious but ultimately natural traveller from beyond the stars. Either way, December 19th will deliver an answer, one that will shape how we look at the next object that crosses into our solar system and how we define what it means to be alone in the universe. Public interest in 3i Atlas is rising fast as the December 19th approach draws nearer. The mainstream press has kept a careful, measured tone, emphasising that there's no threat to Earth and that NASA's investigation remains strictly scientific. But outside those headlines, the conversation is far less restrained. Across social media, online forums, and independent news outlets, speculation has taken on a life of its own. Some frame Atlas as a breakthrough in interstellar science, the next great discovery after Oumuamua. Others spiral toward apocalyptic theories, alien probes, secret government contacts, or deliberate targeting of Earth. Ironically, NASA's policy of silence meant to prevent misinformation has only deepened the public's hunger for answers. In the absence of information, speculation fills the void. If you've followed this entire journey, from the activation of planetary defense protocols, through the formation of secretive task forces, to the cascade of anomalies that challenge everything we thought we knew, then you already understand what's at stake. So if you'd like to stay with this story as it unfolds, subscribe, and share your thoughts below. Do you believe NASA knows more than it's saying? Or will December 19th simply come and go, another data point in a long list of cosmic mysteries? Because the countdown has begun. The telescopes are ready, the protocols are active, and in 6 weeks, when 3B Atlas sweeps past Earth at 267 million kilometres, we'll finally see what's been hiding in plain sight. Whether that moment brings answers or new questions, one thing is certain. NASA's response tells us this is no ordinary comet. The math is clear, the anomalies are real, and if there's something inside that comet-shaped object, something that's been watching, waiting, or simply passing through, then December 19th is when we'll find out. Sweet dreams.